In this video, I'm going to discuss Pulley Lab. So these are the pulley. Pulley is a device to change the direction of a force that you exert on. So you can pull down instead of pulling up, for example, in this picture, you see. Or if you use the movable pulley, something like this, movable pulley, you can get a mechanical advantage. So in this lab, we're going to use the pulley, and you use the idea of concept with the tension force. And here is the type of pulley. Fixed pulley is the pulley that's fixed. So you put the rope around the pulley and you pull it in whatever the direction that works for you. And then this is the movable pulley. Movable pulley is not fixed, so it can go, in this case, up and down. And when you have a movable pulley, you see that you're supporting this 100 Newton weight with the two ropes. So you see that force is, if this is a 100 Newton, but since you're pulling it with it's the same rope, but it's almost like you're pulling with the two ropes. So tension force is now divided into a half, 50 Newton. If you have a fixed pulley, you only supporting with the one rope. So 100 Newton weight, you're going to still support with the 100 Newton. Compound pulley, we're going to do this, but you have a fixed pulley and a movable pulley. So this is the fixed pulley and a movable pulley. What you see on the screen now is your pulley preparation worksheet. So here it has information about pulley. Pulley is a device that looks like a wheel, and you can use the pulley to accomplish three things. Because it's just you use the rope, so it's easier to pull, and it makes. So here, you can use a pulley to make it easier to pull a rope, change the direction of a force, right? And if you use a movable pulley, you can get more mechanical advantage to lift things up. So what is the fixed pulley? Fixed pulley is to use the rope to pull the object, and it changes the direction. Change the direction of a force. In physics, we assume this pulley that you just saw in the image, and physical pulley too, we assume that there is no friction force. So it rotates the pulley wheel rotates smoothly, smoothly, and the rope, there's no friction force. In reality, it's not the case. So draw a fixed pulley diagram, and this FBD, this is a force diagram. So let's see, I can draw something like this. You could have a edge, and then here is a pulley. I have a wheel here, and then a vertical wall. The rope, is hanged to change its direction, and object let's say like this, mass. So the force, we want to write a force diagram. So it's a force is going to be, there's always going to be gravitational force vertically downwards, Fg. And in this case, this object is supported by the rope, upward tension force. And if it's the same rope, throughout the rope, you're going to have the same tension force. You can't have if it's the same rope, you cannot have a different tension force. Tension force is always the same along it. So this is going to be tension force at this location. Okay, the same tension force. What is the tension force? It's going to be equal to the magnitude of a gravitational force. So what does the movable pulley accomplish? I'll say to change that direction. So it makes it easier to exert force in whatever the direction that you desire. What is a movable pulley? Movable pulley is the one that gives all of this still applies. That applies. And also to give some mechanical advantage, right? Let's see, draw movable pulley. And again, this is a force diagram. In this case, the movable pulley will look something like, let's see. Simple looking one. I want to do the simple looking one. So it might be like this. So it could be just like that. And I could have a rope. That's connected here, going around and around. And the object is hanging like this. That's M. Then what happens? You're always going to have a gravitational force vertically downward, Fg. But since you see here, it's the same rope, one rope, but then it looks like it's supported by the two ropes. So in this case, we're going to have a tension force that's upward, and this tension force is going to be Fg half. So that's why you see that movable pulley is used for, mostly used to give to provide the mechanical advantage. In this case, we can tension forces, you can just support with the 1/2 of the weight by using the movable pulley. So let's do this diagram. Is this first one, is this a fixed pulley or movable pulley? That's a fixed pulley. Then what we have is that we have a 10 Newton down. What do you think the scale would read? Let's see. Tension force should be 10 Newton. Therefore, the scale should read 10 Newton. What happens to this one? Now we have two pulleys. Are these pulleys fixed pulley or movable pulley? These pulleys are fixed pulleys. Fixed. And each one of them has 10 Newton. Therefore, tension force here. So we have a tension force T. That's going to be 10 Newton. Wait, so 10 Newton here, then it should be 10 Newton. 10 Newton here. Therefore, 10 Newton here. What does scale read? Scale read also 10 Newton. Look at the first example here. We have a 10 Newton, 10 Newton. But you see the other side? What do you think? How much is this pulling the wall, vertical wall? It should be pulling with the 10 Newton. So here, it's going to be pulling 10 Newton. So when you look at this, this diagram here, copy, paste. Doesn't do it. This part is identical to the one here to the left. So the left-hand side, this part, it could be just a 10 Newton weight, or you could have a vertical wall. It doesn't really matter to the scale point of view as long as it's been supported, and it can only support whatever that the other object can exert a force by following the Newton's third law. So as long as it's supporting the 10 Newton, scale will read 10 Newton. This is true when you measure, when you scale the regular object too by using a scale, right? I might be pulling a 10 Newton here down, but then my other hand is supporting 10 Newton up. So that's what the scale is reading, 10 Newton down, 10 Newton up. I have to support the 10 Newton up for this scales to measure that 10 Newton. So it's just 10 Newton down vertically or 10 Newton horizontally. So the scale in the second example should read 10 Newton. The last example. Now we have 10 Newton weight. And is this pulley fixed pulley or movable pulley? This pulley is movable pulley. Therefore, you see that tension force, it's supported by two tension force. It's the same rope, but it's supported by two tension force. Therefore, tension force will be 5 Newton, and the scale will read 5 Newton. Okay, so that's the pulley prep. and you're going to do the Pulley Lab. So this is our Pulley Lab report that you're going to work on. I'm going to just briefly go over. I'm not going to discuss everything. It's pretty straightforward, I believe. So first, you're going to watch the first two videos to write your measurement from the video. And measure the mass one, which is the collection of toys. And let's see. So here is the list of our Pulley Lab videos, and you're going to highlight this, and then this is the video, the first video. Here I have a scale, and right now it's calibrated to be 0 gram. It's in gram. So I'm going to start putting stuff on it and see how much they're all going to weigh together. So now with this dinosaur, it's 130 gram. I'm going to put narwhal, 261. I'm going to put this bus, that's 414. Why don't I put an Ariel in the group? So that's about 513 gram, and I'm gonna put a bag here to put in. That all together makes it, okay, so this is how much the stuff is, okay, all together makes it 544 gram. Daddy. So you see that you saw it was a 544 gram. What are you going to write on observation M1 here? Make sure you could either write down 544 gram or 0.544 kilogram. So do the same for observation M2. I feel like I did a good job for finding a toy with them. You're going to see. So you're going to also make a measurement for the M2, the different collection of toys. Okay. And the C, that's the video too. And in C, I want you to predict if you were to hang this collection toy one. So this is the collection one. M1. If I hang it like this, just simply downward, what does the measure will read? Well, it's pretty simple. You have a mass that you already found, and then G, which is the gravitational acceleration, which is 10 meters per second square. You can just use 10 meters per second square. If you really want, you can use 9.8 meters per second square, but always write your work. Always show your work. So it was like show work. Okay. And here, as it mentioned, right, mass is in kilogram. So I use the kilogram. So your prediction, for example, for the first one should look like it should measure 0.544 kilogram times 10 meter per second square. It's going to be 5.44 Newton, something like that. Okay. So this is what your prediction. This is going to be your prediction for M1, the collection toy 1. And you're going to do the same thing for the M2. FG1, this is FG1. You're going to do the same thing for FG2. All right. After you've done this, then you watch the video 3 to actually see what I measure using the scale. And watch video 4, video 5, record data. what you see that compare your results from here, right? These two, compare your results, predictions, these prediction, compare. Oops, don't know why that came here. And prediction here. And then make a discussion. Next one, it's pretty straightforward. Now you're gonna see unfortunately, you need to figure out typically, but you can't. So you're gonna see that instead of a string is pulled over, attached mass M1 showing a figure, predict that what reading will be on each scale shown in a figure. So you're gonna see that what's this? Let's see. This is gonna be the scale 1, scale 2. So what's the scale 1 would read? Scale 2 should read. You're gonna make a prediction. This is gonna be toy 1, toy 2. If you were to do this in the lab, and then you see in a video, you will see in this video 6 here, I actually had to add extra scale on the other side. Explain why you had to add the extra scale on both sides. Okay, please explain. So you make a prediction first from this figure. What should the scale 1 should read here? And then what should the scale 2 should read? Then you watch video 6 here. Watch video 6 and then write observation. What actually you see, that actual value of scale 1, scale 2. And the actual experiment, you had to add extra spring scale on both sides. Explain here. All right, so that's the one part of the lab. Next, now we want to have a collection 2 that's hanging. Toy 2 hanging a cord like this, and then predict the reading of a scale. So I want you to now predict the reading of a scale here. Scale. What does the scale read? How does the reading compare to, what do you think about the F2 should be? And also predict us both scale and F2, the force. Also predict F1, and then compare. Are they going to be the same or different? Make a discussion. Okay, so this is the prediction part. Then watch the video. Okay. Then another one is to, instead of a hanging like this, now you're going to connect the both ends attached to one. So predict what is the scales going to read. Are they going to be changed? Both of them, you're going to make prediction. Then you're going to set up this, both these two configuration, this configuration G and configuration H. And you don't get to do it, so you're going to watch the video. And video 8 to record your data, observation for configuration G. So you're going to see what's the scale, F1 and F2. You're going to write down these values and then make a discussion compared to your prediction. Sorry, compared to your prediction in G. All right, so write down the value. Scale 1, scale 2, F1, F2, write down all these values and then make a comparison. Same thing with watch video 9 and then what is the scale actually read. And then make a discussion, here, make a discussion, compare to your prediction. In H. Okay, so you're going to make a comparison. So these are the lab measurement, and then you're going to make a discussion. Finally, consider the pulley arrangement shown in the figure here in J. How does the force F compared with the weight of a mass 2? See, this is the mass 2, which is the toy collection of a 2. So compare F versus FG2 versus FG2. Compare this and what you make your prediction. What does the F would read? And you make a prediction and then you make a discussion. Always show your work. And then make sure you write your conclusion clearly. What's the unit this has to be? Newton. Make sure you always have a unit written, correct one, okay? So that's for the J, and then you're going to watch the video 10. Watch the video 10 and record your data. You're going to write down the observation. So what actual value of a F it was? What was it? And then you're also going to make a discussion, compare your experimental predicted value in J, predicted value in J, and then make a discussion. All right, so that is going to be the end of our lab part. And at the end, I am going to ask you to make a diagram. Can you make an apparatus? Can you make an apparatus for force will be 1/3 or 1/4 of the weight of the hanging mass. Draw such settings. So trying to figure out if you can do that 1/3, 1/3, or 1/4. We'll see if you can make such a device. If you get the correct one, you might get the extra credit. So I hope, so this lab should be straightforward, and then I hope you enjoy the lab, and I will see you in the class.